Cool. Okay. Group 5. What did you observe?
We observed that like the glow of the light bulbs, it went away pretty quickly. And then we saw that the deflection of the second light bulb was clockwise.
Okay. The deflection of the second in the compass was clockwise, and that meant that that's what you indicated was the current coming, or the direction of the current. Did you also check L1, or is that a guess on your part?
We just like guessed that. We weren't sure yet.
That part. Okay, cool. Any thoughts about why things were transient?
We weren't like completely sure, but we thought it might have something to do with like the capacitor.
The capacitor? Yeah, for sure. Yeah, that's the only thing new that's in the circuit. Yeah, absolutely. It is a capacitor for sure. Yeah, that's a good start. Elliot, you had something you want to say?
Never mind. Sorry.
Never mind. Sorry. Got it.
Yeah.
Okay, group 4. What did you see?
Yeah, we saw a counterclockwise deflection. And yeah, as was mentioned previously, the brightness of the bulbs and hence the current slowly went down. And so could that mean that the capacitor is basically like a resistor that increases in resistance over time? Or
Ooh, interesting. So maybe it's a changing resistance. Possible. I like that. That's an interesting idea, right? Like if you, okay, cool. No, that's interesting. Anything else in group 4 that you guys want to add to this? Awesome. Group 3.
We observed glow. Ours deflected clockwise. I think another group's deflected counterclockwise. I'm not sure why, but and then the glow for me, it was transient the first time, but then I couldn't get it to like do that again. Like it wouldn't fade like anymore when I like connected the circuit again. It was just like it was still on. It was like constant.
Fade. That is fascinating. Okay. Well, either you burnt your capacitor, unlikely, but possible. So I want to go back to something that Lowell just mentioned, because I want to make sure that there's clarity in everybody's mind. Some groups found the deflection to be clockwise, and some groups found the deflection to be counterclockwise, but everybody's making the current go in the same direction. So are we crazy? Like, did we just all copy one of each other's board, or like what's going on? Yeah, Elliot. And then Isabel after that.
I mean, I'm not entirely sure because I didn't get mine to totally work. But I think it's just that, like, normally whenever we're drawing current, like we all, like in the stuff we did today at least, we all had it going one direction.
Right.
So they might have just done that by like instinct or something.
It's called inertia for drawing. Isabel, what do you think?
It could also be how people put their compasses. Like, everyone was probably looking at the drawing, but may have like seen the drawing and then done something different, or their wires got mixed up or something like that. Because it doesn't actually, the way the compass moves mostly just has to do with which end of the wire is going through the south side. So
Thank you. Yes. So it doesn't matter whether you're going clockwise or counterclockwise, as long as you're paying attention to which side is connected to the north and which side is connected to the south, right? If your current is going in if you observe a clockwise deflection, then you know that the electrons are entering the south and leaving the north. If you have a counterclockwise deflection, you know that the electrons are entering the north, leaving the south. And that depending on which direction your desk is facing, which means like which one it's easier for you to like put the wire over the compass, you're gonna get, you could get one deflection or the other, but you should be clear about the direction in which your compass is going, right? So clockwise deflection means that you're going the same direction from south to north, so that's the direction of your current. If you get a counterclockwise direction, you know you're going from north to south, and that's just what it is. Whatever the direction north-south is going for your circuit. So that's why, and not to belittle Elliot's point, which is true, every single circuit we've done so far, every single one goes in that direction. So it is also possible that people are just drawing that because that's what we've been drawing for the last 6 weeks, and why not? Cool. Group number 2. Any thoughts?
I mean, I can talk a little bit about it. I didn't have a capacitor, but something that stood out to me is probably the arrowheads, and I did like a little bit of research about capacitor or the capacitor, and it's supposed to be something that stores energy, and when the wire is charged, it can charge the circuit at any time after it's charged back up. And then what confused me the most was the arrowheads, because if the same amount of current is flowing through each of those wires, I would be confused on why it gets dimmer each time. So like,
No,
it
thank you
just doesn't make
thank
any
you for
sense.
thinking on your feet, right? Like, and that's part of it is my mistake. Like in I need to be better about choosing my words. I said, I think orally I said find the direction of the current, but I think on the slide it said like put the arrowhead on the slide. And how can you put arrowheads on the slide when the current keeps changing intensity, right? Like, is it 3? Is it 2? Is it 1? Like, and there's no way for you to answer that question because it keeps changing the whole time. So yeah, thank you for thinking through, and we will use your research in about 5 minutes. So that's gonna be good. Okay, and then anything else you wanted to add? Was anybody even there? Sounds like
I don't think any of us got it to
Yeah,
work.
we were all struggling to get ours to work.
Like,
Oh, I
By the
see.
time we got it to work, the breakout room was closing.
Oh, unfairness. Okay.
But
Yeah.
I can
But-
still. What I was gonna say earlier was, for like was the glow sustained or transient? Well, like at first it was transient, but like I've gotten one to work.
Yeah.
I don't know what that is, but now it doesn't fade.
He broke it.
And like when I touched the same wire, it doesn't fade at all, and I can't get it to go back, so it's sustained now.
I'm not exactly sure what's going on.
Transient.
Cool. Okay, so let's think about this. So let's take a right. So we have, actually let's take a clean wire. So what we have is the battery, and we know that when let's see, annotate. There we go. Okay. So draw this one. Thank you. So we know that there's a glow. If there's a glow, there's a current. And we know the current always leads from the negative end, this way, right? So the current's going this way, the current's going that way, the current's going over here. What is happening here? Natalia, what is going on through the capacitor?
Well, isn't it like charging, I guess?
Okay. It's charging. Yeah, that's what we said it was doing. It was charging. Question to you, Natalia. Can the current go through the capacitor?
No, wasn't it like an insulator or something like that?
Yes, thank you for paying attention. Kian.
I was gonna say what she said.
Okay, so yeah, there's an insulator here, right? Which means the charges cannot go through the capacitor. Which means our circuit is what?
It's
Okay.
closed, right? It's incomplete. It's not a circle.
Incomplete. So how are we getting a current in the first place? Like that's magic, right? Like a little bit. Not only is there current going through the bottom end, but we also saw stuff happening at the top. So there must be a current. Question, is it going this way or is it going that way? Right? The end of the story is it turns out that the current is going, eraser, please. There we are, right? The current is actually also going in that direction this way. So again, like I want you guys to look at this and not just say, well, it's the same. Isn't that just the same thing we've done always? It's like one arrow, right? One arrow that's going like from here, right? And then one arrow going through there like that. Isn't that what we've always done? And I want you to hear like really, really well, there is nothing going on through the capacitor. Like nothing is going on through the capacitor. So how is this even possible, right? Well, if you're an electron, right, you're leaving you're leaving the battery and you're moving, right? And eventually you just end up being stuck to this end over here. And then the next electron, right, is leaving and gets stuck over here. And then the next electron, and the next, and the next. The problem is, and this is something you might have heard in middle school or not, like charges repel, opposite charges attract. Does that ring a bell? Like people have heard something like that. So what that means is the more electrons I add to this end, right? The more electrons I add to this end, the more they're going to do what? They're going to repel, which means that, but where can they go? Where's the only place they can go? Back. Which means the more electrons I add up here, the more they're going to start going backwards. Right? Because they don't want to be stuck on that plate. And at some point, the push going back is going to be exactly equal to the push going forward. And at that point, what's going to happen?
Stop.
They're going to stop. At that point, we lost our current. Yeah, Isabel.
I'm just wondering why at the beginning you said that yours would take longer than ours.
Yeah, my capacitor, so yours, if you look at your capacitor, it says on the side that it's like 25,000, some weird unit, microfarads. My capacitor is 100,000 microfarads. So mine is bigger, and therefore it takes more charges to load it up. To get to that place where like charges are pushing back equally hard, it takes longer, and so it takes longer for mine to charge than it took for yours. No.
So if the currents coming back like meet the currents like coming from the batteries, why would we lose the current? Like why wouldn't
Well, it's not so much that the electrons are coming back as much as there's a, if you think about what's the battery, what is a current? A current is just a flow of electrons that are moving. In order to make anything move, you need to apply a force. So we have in the regular current, in a regular circuit, there's a force that's pushing the electrons out of the battery through the negative end. And that force keeps pushing everything around the circuit. Now, the more electrons you put on the capacitor on the bottom plate, the bigger that force is going to become, but going the opposite direction. When the two forces are equally strong, then the stuff stops moving, right? You get to the balanced situation. That's what we saw with forces. So when the force pushing from the battery is equal to the force coming back from the capacitor, then things stops to move. At that point, you lost your current. So it's not that there's a flow going back, there's just a force that's preventing the electrons from moving forward. Ramsey, and then Natalia.
So then what does charging and discharging have to have like, how come when you charge it and then you touch it again, it lights up back over again?
That's a great question. So and that for that I need the second half of what's going on. So this is what's going on the bottom plate, right? On the top plate we have electrons, and we just saw that the electrons are going in that arrow, which means electrons must be going here and then going back to the battery, right? So that means that somehow what I'm doing is I had electrons, right? I have electrons and they're all flowing back this way to the battery, right? But again, those electrons, so they're flowing to the battery and then through the battery to the other end. And at some point, those electrons, they can't flow forward anymore because there's a counterpart from, so the same way that these electrons from the battery get pushed back, well, the electrons that are coming from the top plate get pushed back, and again, it stops moving. So what you've done here is, if you think about it, if you think about what would be the best way, right? The best way to represent that probably would be something like this. At the beginning, right? At the beginning, there was equal amounts of charges on both sides. That's when your capacitor was neutral. Then what I did is I start taking charges, right? So maybe I take these charges and I add them over here. And then I take these charges and I add them over there. And I take these charges and I add them over there. And I take these charges and I add them over there. And at which point I'm stuck. Like there are just too many charges on that capacitor. It stops moving. When I discharge, when I put a wire from here to here, those extra charges, they just go back where they came from. And now your capacitor is back to normal and you can restart the process. So that's the discharging part. Natalia, you had a question.
Yeah, I had more of like a safety question.
Yeah.
When I recharge it, like I always get a spark. Is that
Yeah.
safe? Because other people don't get that.
It's safe. Yeah, again, like
Okay.
you're dealing with like 6 volts and like very small currents. If this was like a car battery, I wouldn't say no, maybe that's not safe, but like this is totally safe. You're totally fine. Elliot, you had a question.
Yeah, you said that there was electrons on the top slate
Yeah.
of the thing, but how'd they get there if there's
Yeah,
insulator in between?
it's because everything is made of electrons, right? Everything has electrons. You have electrons, I have electrons, the wires have electrons, right? Everything has electrons. Some of us, our electrons can't move, like my electrons and your electrons, they can't move. But for a metal, which is what being a conductor is, those electrons can move. So everything in the circuit has electrons, right? Normally they just stay put until you put a battery, which provides energy for them to move, right? So again, the idea is that when you have a capacitor, right? When you have a capacitor and you're charging your capacitor, what you're doing is you're taking the charges, you're moving them over here and stacking them up this way. And then you're taking charges that used to be here and moving them around. And at some point it stops. When you discharge, right? So now what we're gonna do is we're gonna do the next experiment.